All right, in this video, the second part of chapter 19, we are going to cover 19.3 and 19.4. So in this first section, we're going to talk about preparing aldehydes and ketones. A lot of this is review, and so we will go over it quickly, but especially if your background on alcohols is weak, the oxidation reactions are an important way to be able to make aldehydes and ketones, so make sure to pay attention to those. So the first one, yes, here we go. We're going to go through the oxidations. So I think the slides do aldehydes first and then ketones. I'm going to group them a little bit differently. You group them however you like. All right, so I'm going to do aldehydes and then ketones this way. Okay, so for the aldehyde oxidation, what you're going to start with is a primary alcohol, OH, so you can have an R group here. And it's important that you have a primary alcohol here. You want to use a partial oxidation reagent or a weaker oxidation reagent. There's a bunch of different examples on this slide. The one that you will see from me and most frequently and in your homework would be PCC, pyridinium chlorochromate. It takes you to an aldehyde without oxidizing further to a carboxylic acid. To get a ketone, you're going to take any old secondary alcohol. And with the ketone, because it can't oxidize, or since a secondary alcohol cannot oxidize past a ketone, you can use PCC, or you can also use strong oxidizing agents like sodium dichromate in sulfuric acid with water. You could use your KMNO4 solution. There's a few different options, but with secondary alcohols, you just need something that's going to oxidize, and it will stop at a ketone. PCC, really, really important reagent for making an aldehyde. And those are our oxidations there. We also have ozonolysis. So if you want to make an aldehyde in ozonolysis, what you need are hydrogens, right? So if you are trying to make aldehydes this way and decrease the length of a carbon bond, you need to have at least one hydrogen, right? So you are going to take, in the first step, O3, in the second step, a reducing agent. We usually use DMS in the ozonolysis of alkenes, and that is going to leave you with whatever these are, aldehydes, right? So if they're the two R groups, there would be 2 moles of product. If the R groups are different, then you would make 2 different products, right? Now, to make a ketone this way, you just need to have not a hydrogen. So you could also wind up with a mixture of ketones and aldehydes, just depending on what your substituents are on either side of the alkene. It's still going to be ozonolysis, ozone followed by DMS. And when you are telling me reactions, if it is a 1-step, 2-step reaction, you need to put the 1 in the 2. Otherwise, you're saying you're just mixing it all together, and either that won't work or something else might happen. So you're going to make ketones and aldehydes this way as well, right? And whether it's a ketone or an aldehyde, again, just depends on what is attached to your double bond. There's an alkyne reaction here, so we'll keep going down this way. We're going to look at, let's see, this is going to be our alkyne hydrolysis. So if we're trying to make an aldehyde, what we're looking for is a terminal alkyne. Can't do this with an internal one. And you're going to use hydroboration oxidation. Now, I usually just put BH3. A lot of times with the alkyne hydroboration oxidation, you have an alkyl substituted boron, maybe cyamyl borane, or B2H6. It will be boron containing. And the second step will be peroxide and hydroxide. And for that, you would make an aldehyde, right? It's anti-Markovnikov. It makes an enol, which is typically unstable, and it tautomerizes to a ketone or an aldehyde. If you're trying to make a ketone, you can use this reaction on an internal alkyne. Or if you have a terminal alkyne and you want the ketone, you can use mercury sulfate, sulfuric acid, and water. And this one gives you the Markovnikov product. Again, it gives you an enol that is not stable and tautomerizes to the ketone. All organic one stuff here. So then you go into ketone preparation. We already talked about your strong oxidizing agent. We talked about ozonolysis. We talked about this acid catalyzed hydration of an alkyne. And then I'm not going to review this one with you because we literally just covered it. The Friedel-Crafts acylation. All right, this is another way to get a carbonyl, particularly at the benzylic position. Good things to remember for synthesis. Now, the reactions we're going to do, so with those, that's how you prepare a ketone. But then in an aldehyde, what can we do with a ketone and an aldehyde? So the rest of this, the majority of this chapter focuses on nucleophilic addition reactions. Something that is important to note is that aldehydes and ketones don't have good leaving groups. That is one of the biggest differences between chapter 19 and 20. The reactivity for the aldehydes and ketones is the same. One might be faster or slower than the other, but they're going to give the same types of products in a lot of these reactions. So I want to make note here and make sure that you understand, I'm going to use acetone a lot. I'm going to use acetone as my example because it is the easiest one to draw. I don't even have to write the letter H. But I could easily have used formaldehyde. I could use larger ketones. I could use larger aldehydes. But acetone is the one that I typically will use for examples. Klein does that as well. So what we want to talk about here, we're going to have something adding to this functional group. And we're going to look at a variety of nucleophiles. Nucleophiles are so attracted to carbonyls because, one, you have the inductive effect. Oxygen is more electronegative than carbon, so it's pulling that electron density away from the carbon. And you also have resonance. So while this might be a minor resonance contributor, it is a contributor. And it really helps us to see that positive charge on that carbonyl carbon. And we are going to attack this guy over and over and over again. Stereochemistry, we don't focus on as much in these reactions because the electrophile that we are attacking is flat, right? So the nucleophile could attack from the top or the bottom, and you're going to make something tetrahedral. If it is chiral, you will often get racemic mixtures, so you won't be focused on stereochemistry as much in these reactions. Now, here there's a little bit of discussion about the difference between ketones and aldehydes. Since aldehydes are less sterically hindered, sometimes they may react more quickly. The electronic effects, you're not getting that electron density from another R group. But again, these are going to react very in very much the same way. So you really don't have to worry about this note here. We're going to be looking at a lot of reactions and mechanisms, and while on a multiple choice test I may not ask you to draw out a mechanism, I will ask you questions about the mechanism. So we are still going to be going through them. And something that you should write down, I'll write it down, it's here. You need to pay attention to your reagents. If you're in an acidic environment, don't bring up a hydroxide if you need to move a proton. If we're dealing with a strong base, and a lot of our nucleophiles are basic, like the Grignard, then you should not have H plus hanging around. You've got to pay attention. All right, so we will be looking at reactions that proceed both in acidic conditions and basic conditions. We will go over the Grignard reaction again in this chapter. We will also see it in the next chapter. You've now had it in Organic 1. I have reviewed it at the beginning of this semester. It will be in chapter 19. Chapter 20, you can bet that there are going to be questions over the Grignard. Now, I don't always like to hover here, but I do think there's a couple of things that are important that we can note about the mechanisms you're going to see before we get into specific reagents. There is going to be a lot around these two steps depending on what reagents we're using, but we are going to see a nucleophile attack a carbonyl over and over again. This will always result in pushing a pair of electrons up onto the oxygen and making a tetrahedral intermediate. You will hear me say the term tetrahedral intermediate an unacceptable amount of times, but this 2-arrow step is something you need to get comfortable with. You cannot have any sort of SN2, so you should not be attacking a carbonyl and something leaving at the same time. You will always be attacking, pushing out onto the oxygen, tetrahedral intermediate. A lot of our reagents, if they're not in acid, will require some sort of water or H3O plus workup, because we are going to be making alcohols in some of these reactions. When we are dealing with mechanisms, you may see in the notes, in the slides, in some of my upcoming videos, that when we're dealing with acidic conditions, there's a few different ways that we can represent. You could show the exact acid that's being used, like sulfuric or nitric, or you can use HA, and that's just going to be acid, and then the generic, A minus would be the conjugate base. You could use H3O plus, because even in a concentrated acid, there's going to be some water. And you have H2O, and you have H plus around. These are all things that you can use. OH minus will not be there. Do not bring OH minus in. If you need a base, water is your friend. Okay, so you may see this abbreviation as we go forward. So I want you to now that I've ranted about acids, I want you to think about the difference between the basic conditions versus acidic conditions. It's the same two steps, a nucleophilic attack and then a proton transfer, or just in the opposite order. Under acidic conditions, we often don't have as strong of a nucleophile, so the protonation happens first. When this happens, this is an even stronger electrophile. The plus charge on the oxygen causes it to pull electron density even harder. And so there, even a weaker nucleophile could now attack. It's the same basic steps. You are still going to attack, push electrons to the oxygen, tetrahedral product or intermediate. Okay, so what I was just saying about the powerful electrophile here is just a picture of the resonance to hopefully convince you that it makes this a stronger electrophile. Puts a formal positive charge on it, so of course it is more electron poor. Now, this is a weird slide. This is not a reaction that you need to know. So what we're going to be looking at is nucleophiles that can add, but then aren't such good leaving groups that it could just go backwards. So we're not going to see halogens acting as nucleophiles. We're going to see oxygen, sulfur, nitrogen, hydrogen, and carbon. That's where our little Grignard shows up again. We're going to do Wittig. You've seen that in lab. There's a lot to cover here. There's going to be some similarities as well. There are going to be some mechanisms that I hold you responsible for. There's going to be some that are not. It's important to watch through the videos and take some notes. In the next video, we will cover oxygen nucleophiles.